In the last class, we have seen regular expressions as formal representations for languages. Today, we are going to see the class of languages generated by the family of regular expressions. For this, we can have a claim saying that the class of languages generated by the family of regular expressions is precisely the set of regular languages. And to prove this, there are two cases. The first case is that any regular expression is representing a regular language. And the case 2 is that for any regular language, we can have a regular expression. So we will prove this claim using two subclaims. The first claim is that the language generated by a regular expression is regular language. Claim number 2. Any regular language can be generated by a regular expression. And the proofs of subclaim 1 and 2 are sufficient to prove the claim, because subclaim 1 proves that the language generated by an arbitrary regular expression is a regular language. And subclaim 2 tells us that an arbitrary regular language can be generated by a regular expression. In this lecture, we are going to see the proof for subclaim 1, and in the next lecture, we shall prove subclaim 2. So subclaim 1 is that the language generated by a regular expression is a regular language. And we are going to discuss a constructive proof for this claim. And the construction is, given a regular expression R, one can construct an N of A with epsilon transition AR, N of A from R, such that the language of the constructed N of A is same as the language of the regular expression. If that is the case, that means there exists an N of A for a language represented by an arbitrary regular expression, and hence the language generated by any regular expression is a regular language because of the existence of an N of A. And before we discuss the algorithm, we need to discuss a generic representation for a regular language. First, the N of A with a single start state. We have seen a lemma in a previous class that an N of A with a number of start states can be converted into an equivalent N of A with a single start state. The proof we have seen already. Revisit it. For example, suppose you are given with this N of A. There are two start states P and R. You can convert it into an equivalent N of A with only one start state, which is the newly added start state. And what we did is that we added a new start state and we added epsilon transitions to the existing start states of the given N of A. So we removed the start state status of P and R. We added a new start state and added epsilon transitions. And it is easy to observe that the language is same with a single start state. Formally, we construct this new N of A with the new state set as the previous state set union this new state. And the new states, only the new state is set as the start state. And transitions, new set of transitions is the set of all existing transitions, that is delta, union these newly added red transitions. That is, for each initial state P in the given N of A, you add a transition from the newly added start state to P with the label as epsilon. That's what we did. Okay, so we can have an N of A with a single start state. If the given N of A is having more than one start state, this is what we do to obtain a N of A with a single start state. Similarly, given an N of A with multiple final states, one can construct an equivalent N of A with a single final state. A very similar construction. Look at an example. Here is an N of A, here is an N of A given which is having a single start state and two final states, and we are going to convert it into an equivalent N of A with only one final state. This is what we do. So what we did is that we added epsilon transitions to a newly added final state, and we removed the final state status of the existing final states. So what we did, suppose this N of A is accepting by ending in R. This N of A can accept the same string by ending in F by taking the epsilon transition. Similarly from T as well. Formally, what we did is we added a single initial state to the existing set of states and made it as the only final state. See, only final state. And to the existing transitions, we added these new epsilon edges. From all the existing final state P in F, these two, in this particular case, add an epsilon transition from a final state to the newly added final state with the label as epsilon. So that's what we did. So with this, we can have a lemma saying that without loss of generality, one can assume that any regular language can be represented by an N of A with epsilon transitions having only a single initial state and a single final state. Why we say without loss of generality? Because if the given N of A is having more than one initial state, we know what to do to obtain an N of A with a single initial state without changing the language. Similarly, we know what to do if there are more than one final states. So this tells us that a regular language can be represented by an N of A like this. Given language is regular means there exists an N of A with a single initial state and a single final state for accepting the language. And the other part of the N of A is not visible. Could be anything depending on the language. So the only thing we need is this kind of a generic representation of an N of A for an arbitrary regular language. So now, whenever we say the language is regular, that means there exists an N of A of this structure with a single initial state and a single final state. And with this, now we can discuss the algorithm to generate an N of A with epsilon transitions from a regular expression. For that, first recollect the definition of regular expressions. I am just reproducing it. We have seen it in the last class. A regular expression can be recursively or inductively defined as the base cases are phi and a, where a is an arbitrary input symbol or alphabet. And this is the inductive step. That is, if R1 and R2 are regular expressions, then R1 plus R2 is a regular expression, R1 R2 is a regular expression, or R1 star is a regular expression. We are going to discuss a construction which constructs a regular, an N of A with epsilon transitions from a regular expression. Given a regular expression, one can inductively define or construct an equivalent N of A with epsilon transitions. So first we need to define NFA for the base cases, and then we need to define NFA for the induction step. And basically we are doing an induction on the height of the expression tree. So what is the base case? First base case is this: NFA for R is equal to phi. Phi is the first base case. We know that if the regular expression is phi, then the language is empty set. And this can be the NFA. See that there are no paths going to the final state from the initial state, so the language is empty set. So this could be the NFA for phi. So I am giving you an NFA for this regular expression. The second type of base case is this. Regular expression is an alphabet, and this is the NFA given. See that this NFA is accepting only one string, which is set A, which is the language of the regular expression. So we have regular expressions for the base cases. Now, induction hypothesis is that there exists an NFA for any regular expression of height at most k. Height at most k means height of the expression tree representing the regular expression. If you are not remembering it, please revisit the last lecture and see what is the expression tree. Okay, now let us try to construct regular expression for the rules. First rule is R1 plus R2. So from the induction hypothesis, we know that there exists an NFA for the regular expression R1, which is AR1. And there exists a regular expression for the, an NFA for the regular expression R2, which is AR2, such that AR1 is representing the language of R1 and AR2 is representing the language of R2. These are the NFAs. Then can you suggest a way to obtain the NFA for R1 plus R2? In fact, there are different ways in which you can construct. I am giving you a simple way where I am just adding an epsilon transition from the initial state of the first NFA to the initial state of the second NFA. See the new NFA, what is it doing? It can accept either if the first one is accepting or if the second one is accepting by taking this epsilon transition. Thus this new NFA accepts if and only if either the first NFA accepts or the second NFA accepts. And one can prove the correctness of this construction that the language is precisely the language of R1 plus R2 by applying the method of mathematical induction. So observe it and see the language, and thus we have a way to obtain the NFA for R1 plus R2 from the NFAs for R1 and R2. And the next rule is R1 dot R2. Given NFAs for R1 and R2, AR1 and AR2, how will you construct NFA for R1 concatenated with R2? Do you have any suggestion to do that? So here is a simple way. What I do is I just added an epsilon transition from the previous final state of the final state of the first NFA to the start state of the second NFA, and I just removed the final state status of the first NFA. If I did that, and also I removed the start state status of the second NFA, this is again removed. Now to accept, you have to start from here and you have to go all the way to the final state of the second NFA. By doing that, what you did is you have used a string accepted by the first NFA, that is a string in the first language. And then you took the epsilon transition and you used the string accepted by the second NFA So a string is accepted means it is of the form x concatenated with y such that x is in the language of R1 and y is in the language of R2. So you can observe that new NFA accepts means it is accepted by the first part is accepted by the first NFA and the second part is accepted by the second NFA, or it is of the form xy such that x is in the first language of R1 and y is in the language of R2. Thus the new NFA is accepting the language of R1 concatenated with R2. Here again, one can use the principle of mathematical induction to prove the correctness of this construction. With this, let us move on to the last rule, which is Kleene iteration of star closure, R1 star. So here is the NFA given for R1. From induction hypothesis, we know that AR1 is the NFA for regular expression R1. From this, how will you construct the NFA for R1 star? Any suggestions for that? Here is a simple way of doing it. I add epsilon transitions from the start state to the final state and also from the final state to the start state. And if I take this one and accept, that means I accepted L raised to 0. If L is the language of this, I accepted L raised to 0 by taking this. And doing through this, I can accept L raised to 1. After L raised to 1, if I take this epsilon h back, I can accept L raised to 2 like this. Similarly, I can accept L raised to 3, L raised to 4, etc. So it's very easy to observe that this new NFA is accepting the language of R1, the whole star, and hence we are done. Here again you can use the principle of mathematical induction to prove the correctness of the construction. And with this we are moving on to the last slide where I am giving you an assignment. Apply the algorithm discussed in the class to generate an NFA with epsilon transitions from the following regular expression. So how will you do it? You know that all these are basic regular expressions, just alphabets. So from the step for creating regular expression for the base step, you know how to generate regular expressions for all these base cases. You will get 1, 2, 3, 4, 5 different NFAs. Now use the NFAs for A and B and compile and use the rule to get NFA for A plus B. What do? You add an epsilon transition from the start state of the NFA for A to the start state of the NFA for B. If you add that epsilon transition, you can get an NFA for A plus B. Now, if you have an NFA for A plus B, you know how to construct an NFA for A plus B star. How will you do that? Add an epsilon transition from the start state of this NFA to the final state and from the final state to the start state. You will get an NFA for A plus B star. Now, if you have NFA for this part and this part, you know how to apply the rule for the concatenation. That is, add an epsilon transition from the final state of this NFA to the start state of this NFA. So, you will get the NFA for this part. Now, using the rule for plus, you can combine the NFAs of these two to generate the NFA for this. Now, by applying the rule for concatenation from these two NFAs, you can construct the NFA for the whole regular expression. So, please try it. Just act as a computer and mechanically obtain the NFA. Only if you do it, you can understand the algorithm completely. So, with this, we are finishing this lecture and we have seen how can you construct an NFA with epsilon transition from a regular expression. Thank you.